Good morning, esteemed members of the jury, distinguished guests, and beloved family. I'm deeply honored to be here today to present my doctoral research on application of shape memory alloys as spring actuator or seismic reinforcement of buildings. This journey has been a remarkable exploration into the fascinating world of shape memory alloy. Before I get started, let me outline the plan of my presentation. First of all, I'm going to start with a brief introduction, then an overview of shape memory alloys, then I'm going to move to shape memory effect helical spring case, pseudoelasticity effect building structure case, and finally some conclusions. Throughout history, humans have relied on raw materials like leather, iron, stone, cotton, wood, etc. Over time and through experimentations, these materials have become stronger, more durable, and smarter. In this category of so-called smart materials, three types of coupling are distinguished: piezoelectric material, magnetostrictive material, and thermomechanical material. Piezoelectric material refers to materials that react to the application of an electric field. Magnetostrictive material refers to materials that react to the application of a magnetic field. And finally, the thermomechanical material, which are attributed to shape memory alloys, are highly dependent on temperature. Now let's discover this magical material, shape memory alloy. Shape memory alloys form a class of metallic materials with unique properties. They were first discovered in the 1930s by the Swedish chemist Arne Olander, who first described the ability of the gold-cadmium alloy to recover its original shape after undergoing large deformations. The term alloy refers to a mixture of two or more elements, at least one of which is a metal. For instance, steel, which is a mixture of iron and carbon, and bronze, which is a mixture of copper and tin. Now let's explore the concept of the martensitic transformation, one of the most popular terms in shape memory alloy field. The martensitic transformation is a phase change phenomenon that occurs in certain materials, and it was named after the German metallurgist Adolf Martens, who first described this transformation. According to Guénin's definition, the martensitic transformation is a displacive structural transformation of first order without diffusion, which involves a homogeneous shear strain. The term displacive means the rearrangement of atoms through small, finite, and highly coordinated movements that follow a specific bending angle, and it occurs without any change in density or the volume of the material. Shape memory alloys have two main phases: austenite and martensite. Austenite is symmetric, while martensite is less symmetric. Also, austenite refers to the high temperature phase, while martensite refers to the low temperature phase. The martensitic transformation is controlled by four temperatures: austenite finish, austenite starts, martensite starts, and martensite finish. At temperature above austenite finish, the alloy is 100% austenite, while at temperature below martensite finish, the alloy is 100% martensite. Now, for a better understanding of the martensitic transformation, let's examine this diagram of martensitic phase in relation to temperature. As the temperature increases, the transformation remains in the martensitic phase, until it reaches austenite star temperature. At this point, the martensitic phase begins to transform into austenitic phase until it reaches austenite finish temperature. At this point, the martensitic phase has fully transformed into austenitic phase. Now, when cooling at martensite star temperature, the austenitic phase starts to transform back into a martensitic phase until it reaches martensite finish temperature, where the phase is fully martensitic. Now, let's move to the thermomechanical behavior of shape memory alloys. Shape memory alloys exhibit two significant macroscopic phenomena which called superelasticity and shape memory effects. Superelasticity, also known as pseudoelasticity or pseudoplasticity, designates the capability of recovering the original shape after undergoing large deformations that are induced by pure mechanical loading, and it occurs without any change in temperature. Let's explain this. Here, the alloy is in its original shape in the austenitic phase at temperature above austenite finish. The crystal structure is composed of tiny symmetric squares. This part is purely elastic, where stress and strain are proportional. Now, after the application of an external force, the martensitic transformation begins, and the crystal structure deforms into left and right rhombuses. This phase is called the detwinned martensite, and it is superelastic. Now, after the release of the stress, the martensite begins to transform back into austenites, and the crystal structure returns to the tidy symmetric squares. Another important thing is, if we go beyond point C, the plastic deformation begins, leading to dislocations and eventually irreversible damage. Now, you may be wondering, what is the difference between elasticity and superelasticity, right? To answer this question, let's make a comparison between a copper wire and shape memory alloy wire. For copper wire, if we move the wire a bit and let it go, it returns to its original shape. This is what we call elasticity. But if we go too far, it doesn't return to its original shape. And this is what we call plasticity. Now, for shape memory alloy wire, for small deformations, it shows elasticity. But for extreme deformations, it shows superelasticity. So this is what superelasticity effect looks like in general. Now, let's move to the second property of shape memory alloy, which is shape memory effects. Shape memory effects indicate the ability to recover the original shape by simple heating after being initially mechanically deformed at a low temperature. Let's explain this. First of all, the alloy is in the austenitic phase above austenite finish temperature. When cooling at temperature below martensite finish, the alloy transforms to twinned martensite phase. The macroscopic shape remains unchangeable, and the deformation is equal to 0. After the application of an external force at low constant temperature, the material transforms into detwinned martensite. The macroscopic shape changes, and the deformation is no more equal to 0. After the stress is released, a permanent deformation is observed, and the martensite remains oriented. Finally, when heating at temperature above austenite finish, the material returns to its original shape in the austenitic phase. The question that now rises is, how can we set the memory shape? To answer this question, let's take an example. First of all, we shape the material as needed using screws to hold the wire in place. Then, we place it in the furnace at a really high temperature. The wire transforms into austenites and the memory shape is set. Then, we cool it down at room temperature. The wire transforms into martensites with zigzag pattern. This phase is called twinned martensites because it is composed of symmetric left and right rhombuses. Now, we can bend the wire however we want, and it stays in the martensitic phase, but this time into asymmetric rhombuses. This phase is called the detwinned martensite. Now, if we heat the wire up, it returns to its original shape in the austenitic phase. And it sounds like a magic trick, isn't it? Now let's move to the families of shape memory alloy. There are actually more than 20 families of shape memory alloys, but the three famous ones are nickel-titanium family, copper-based family, and iron-based family. The nickel-titanium family offers many advantages such as the biocompatibility, corrosion resistance, lightweight, and high strength. However, it has some disadvantages, including the high price, the complex thermomechanical behavior, and the manufacturing challenges. For the copper-based family, it is known for its cost effectiveness, ease of fabrication, and small hysteresis, and also great design flexibility. However, they have some disadvantages, including the low ductility, intergranular fracture, and sensitivity to aging. For iron-based family, they are also known for their cost effectiveness, ease of fabrication, and high strength and ductility. However, they have disadvantages, including the lower corrosion resistance and lower shape recovery strains. Now, if we make a brief comparison, in terms of maximum recoverable strain, nickel-titanium offers the highest at 8%, followed by copper-based with a moderate 5%, while ferrous-based shape memory alloys offer a lower maximum recoverable strain, typically less than 5%. In terms of costs, nickel-titanium is the most expensive, followed by copper-based, while ferrous-based is the most cost-effective option. In terms of shape memory effects, the nickel-titanium offers the highest effects, followed by copper-based with a moderate effect, while ferrous-based offers a limited shape memory effect. In general, nickel-titanium remains the most usable alloy in the commercial sector, while ferrous-based shape memory alloys are the most preferable and highly recommended in construction field. Now let's move to the third section, which is shape memory effect helical spring case. In this section, we will focus on the nickel-titanium shape memory alloy using the ORQ model, which is a macroscopic phenomenological model. This model has been chosen for two main reasons. First of all, the reduced number of internal variables, which can be easily found through experimental tests. Secondly, this model is highly compatible and easily integrated into finite element analysis codes. ORQ developed an efficient 3D model for shape memory alloy simulations, where the free energy is set as follows. Where epsilon is the total strain tensor, E is the total deviatoric strain tensor, epsilon TR represents the transformation strain tensor, ETR is the deviatoric transformation strain tensor, theta is the volumetric strain, D is the elastic stiffness of shape memory alloy material, T is the ambient temperature, H is a material parameter related to phase transformation hardening, and of course the indicator function defined as follows. Accordingly, we can write sigma equal the derivative of psi with respect to epsilon, and xtr equal the derivative of psi with respect to etr, where xtr represents the transformation strain tensor. Now, splitting the stress and the strain tensors, we obtain equation 4 and 5, where S is the deviatoric stress, P is the hydrostatic stress, and 1 is the unit tensor. Now, equation 3 can be rewritten like this, where gamma equals 0 if ETR between 0 and epsilon L, and gamma equal or greater to 0 if ETR equal to epsilon L, where epsilon L is the maximum transformation strain. This study was performed using the finite element analysis software ANSYS, which provide us with two significant advantages. First of all, the minimum number of constitutive parameters. Secondly, there is no need to use a user-made subroutine, since the OEQ model is already implemented by default in the ANSYS software library. For the material properties used for simulating the shape memory effect of the helical spring, we have H is the hardening parameter, T is the reference temperature, R is the elastic limit, beta is temperature scaling parameter, M is load dependency parameter, and it represents the asymmetric behavior of shape memory alloy in tension and compression. Epsilon L is the maximum transformation strain, EM is the Martensites-Young modulus, E is Young's modulus, and of course nu is Poisson's ratio. For the geometrical details of the shape memory alloy helical spring, we have coils number n equals 7, wire radius R0 equal to 0.2 millimeters, and the initial pitch angle alpha 0 equals the inverse tangents of L0 over 2p times R0 times n, and it depends on the spring initial length and the coil's radius. Now, to analyze the response of the helical spring in terms of force displacements, 9 different geometries were considered. In each case, we varied the coil radius and the initial length to observe how these parameters influence the spring's behavior. For the initial pitch angle, it was calculated using equation 7 seen previously. The helical springs are assumed to be fixed in their left end, while the right end is subjected to a specific displacement. Now, to analyze the shape memory effect of the helical springs, we used a combination of thermal and mechanical loading following 5 different steps as shown in figure 7. In the first step, we lowered the temperature from 23 degrees Celsius to 5 degrees Celsius, causing a phase change from austenite to twinned martensites. In the second step, at 5 degrees Celsius, we apply a 35 mm tension displacements, causing a phase change from twinned martensites to detwinned martensites. In the third step, the spring is unloaded to 0 displacements while maintaining 5 degrees Celsius. In the fourth step, the spring's temperature is increased to 100 degrees Celsius, causing it to return to the austenite phase. And finally, in order to complete the one-way shape memory effects, the temperature is back to 5 degrees Celsius. The simulation of shape memory effects helical spring was performed using a 3D solid model for each geometry, with meshing using solid 186 structural elements and the tetrahedral method. The simulation results are presented in Figure 6, showing the force displacement curves of the 9 different geometries of the helical springs. When comparing the curves vertically with a constant initial length, it is clear that the maximum force is affected by the coil radius. Increasing the coil radius leads to a decrease in the maximum force. Now, when comparing the curves horizontally with constant coil radius and a variation in the initial length, it seems that the maximum force is not highly affected by the free length, showing only a minimum variation. Now, to further analyze the impact of these two geometric parameters on the spring's behavior, additional parameters like weight, strain, and maximum force were calculated and presented in this table. It is clear that the coil radius of the helical spring has a significant impact, estimated as 97.3% for the weight and 93.6% for the maximum force. On the other hand, it seems that the initial length of the spring has a relatively minor impact, estimated at 2.7% for the weights and only 0.5% for the maximum force. Now let's move to the fourth section, which is superelasticity or pseudoelasticity effect building structure case. In this section, we will focus on how the pseudoelasticity effects can be applied to building structures in order to increase their resistance against seismic events. As you know, earthquakes are common natural disasters that occur in many regions of Earth. They continue to cause severe damage to infrastructures and buildings and to claim thousands of lives every year. Morocco, for instance, has recorded 3 significant earthquakes. Agadir earthquake in 1960 with an amount of 12,000 deaths, Al-Husima earthquake in 2004 with an amount of 629 deaths, and most recently, Al-Haus earthquake in 2023 with an amount of 2,901 deaths. So many engineering solutions have been implemented in order to increase seismic resistance of buildings. The first technique is the classical steel reinforced structures, and it relies mainly on the ductility, flexibility, and lightweight. However, most steel stresses are permanent, which cause large residual deformations that render the structure unusable after an earthquake. The second technique is based on shape memory alloy reinforcements, which, unlike steel, provide tensile recovery when unloaded during earthquakes. It offers significant energy dissipation, and they are quite effective in improving the response of reinforced concrete buildings. The pseudoelastic behavior of shape memory alloy was performed based on 2 types of structures: a simple reinforced concrete frame and a medium-rise 8-story reinforced concrete frame. In the first type, focus was on ferrous-based shape memory alloys, while in the second type, both ferrous-based and shape memory alloy were used. For both cases, the seismic behavior of the structures was evaluated using the nonlinear static analysis, also known as pushover analysis, along with the dynamic time history analysis. For the static pushover analysis, it has become the standard method for seismic assessment of structures. It is used to describe the relationship between shear force and roof displacements, with a monotonically increasing lateral force and constant height distribution. According to the Moroccan Seismic Code RPS 2000, revised version 2011, the total lateral seismic force F should be distributed over the height of the structure as shown in Figure 11, where Ft is the additive force on the top floor, Fn is the horizontal force applied to nth story, and Hn is the height of the nth floor measured from the base. The total lateral seismic force F was calculated using equation 10, where V is the zone velocity coefficient and it's equal to 0.13 meter per second, S is the site coefficient and it's equal to 1.2, D is the dynamic amplification factor, I is the coefficient of priority and it's equal to 1, K is behavior factor equal to, and of course W is the structural load. On the other hand, the dynamic time history analysis, it is without a doubt the most realistic and accurate analysis method. It is also known as nonlinear time history analysis, nonlinear response history analysis, or also the nonlinear dynamic process. It is often used to predict the nonlinear inelastic response of structures subjected to seismic loads. Now for modeling, we start with the simple reinforced concrete frame, where shape memory alloy reinforcements are placed at the plastic hinge area of beam and columns, covering 15% of their initial length, while the rest of the structure is reinforced with ordinary steel bar. The plastic hinge area is the area where beam and columns bend and absorb energy under heavy load or during earthquakes in order to prevent structures from collapsing. For the geometric characteristics, we choose a symmetrical frame of 3 meters of height and 4 meters of bay length, where beam and columns have both square cross-section of 25 by 25 centimeters. A vertical load was applied to the beam and its self-weight is automatically included. Finally, an incremental horizontal force was applied for the pushover analysis. Now for the material properties used in the simple frame structure, 3 types are involved: concrete, steel, and ferrous-based shape memory alloy. Their associated properties are presented in Table 5, and their behavior is modeled using 3 different approaches: the Mander nonlinear model for concrete, the bilinear stress-strain model for steel, and the auricule model for the ferrous-based shape memory alloys. This study was performed using the Seismostruct software, which is an award-winning finite elements package capable of predicting the large displacement behavior of space frames under static or dynamic loading, taking into account both geometric nonlinearities and material elasticity. For the dynamic analysis of the reinforced concrete frame, 5 different earthquakes records were used: Little Greek 1 and 2, San Fernando 1 and 2, and San Francisco. They were calculated and scaled using equation 11, where AS is the scaled acceleration at time t, uppercase A is the desired amplitude of acceleration, Lowercase a is the original acceleration value at time t. A max is the original maximum acceleration value. Also, two seismic accelerations were analyzed. A moderate level at 4 meters per second square and a strong level at 8 meters per second square. Now let's move to the second case study, which is the 8-story reinforced concrete frame. This structure was previously studied by Alam in Canada using the nickel-titanium shaped memory alloy reinforcements and following the National Building Code and the Canadian standards. In our case, we studied a similar structure, but this time in Morocco, using different types of reinforcements, nickel-titanium shaped memory alloy, in addition to ferrous-based shaped memory alloy, following the Eurocode 2 and RPS 2011. These two structures were then compared with the reference building, which was reinforced completely with ordinary steel bars. For the geometric characteristics, we choose a symmetrical layout of 4 bays in each directions, where bay length equal 4.85 meters and height equal to 4 meters. For beams and columns, we choose the following sections. For the material properties used in this medium-rise 8-story, 3 types were involved, as in the previous case: concrete, steel, and shaped memory alloy. But this time, 2 types of nickel-titanium and 2 types of ferrous-based shaped memory alloy were used. Where ferrous-based shaped memory alloy 1 and 2 refers to the following acronyms. Also, this study was performed using Seismostruct software for both static and dynamic analysis. Now, for the dynamic analysis, 3 ground motion records were applied at the bottom nodes of each column using equation 11 for scaling. Now, let's examine the results of this study. Starting from the first case of simple reinforced concrete frame, for static analysis, Figure 16 presents the pushover curves for the 2 frames configurations. When comparing the 2 variants in terms of strength, shaped memory alloy variant is stronger than reinforced concrete one, enhancing the overall structural integrity. In terms of stiffness and rigidity, the reinforced concrete variant is more rigid than shaped memory alloy variants, showing more resistance to deformation. Finally, in terms of ductility and flexibility, the ferrous-based shaped memory alloy variant is more flexible than reinforced concrete one, and it shows high ability to deform plastically without breaking, and also high capacity to absorb energy. Now, Figure 17 shows the damage pattern at collapse states between shaped memory alloy and reinforced concrete variants. As you can see, shaped memory alloy variants distribute damage more uniformly, involving all members, which results in better energy dissipation. While in the reinforced concrete variants, the damage is localized, leaving some areas unaffected, which results in less energy distribution. Now, for the dynamic analysis, Figure 18 and Figure 19 present the total support force and moments, respectively, for the 2 frame variants, and their 5 different ground motion events. As you can see, for both seismic accelerations, A equal 4 and A equal 8, the force and moment demands for the shape memory alloy variants are generally lower than those of the reinforced concrete variants. Now, figure 20 shows the maximum residual drifts defined as the permanent lateral deformation of a building following an earthquake. As you can see, the most severe earthquakes are SF2 and SFR, and they show major deformation and even rupture during the SF2, while the shape memory alloy variants showed better performance and superior recentering capabilities. Moving to the second case study of the 8-story for static analysis, figure 21 presents the pushover curves for the Canadian and the Moroccan buildings. In terms of hierarchy, at both sites, Morocco and Canada, the 5 curves show similarity following the same order. In terms of strength, ferrous-based shape memory alloy is the strongest, followed by steel, nickel titanium 1, nickel titanium 2, and finally ferrous-based shape memory alloy 2. In terms of rigidity, steel exhibits the greatest rigidity, followed by ferrous-based shape memory alloy 2, nickel titanium, and finally ferrous-based shape memory alloy 1 with the lowest rigidity. Now for the dynamic analysis, focus was on displacement results, specifically the maximum residual interstory drifts under both negative and positive ground motion directions. As you can see from figure 22, shape memory alloy reinforcements significantly reduces the maximum residual interstory drifts, showing higher recentering capacities. For instance, nickel titanium reduces the maximum residual interstory drifts by up to 96% for the Canadian building and 86% for the Moroccan one. Similarly, the ferrous-based shape memory alloy reduces the maximum residual interstory drifts by up to 97% for the Canadian building and 19% for the Moroccan building. Now, comparing the nickel titanium shape memory alloy and ferrous-based shape memory alloy, we can say that nickel titanium based shape memory alloy shows slightly better performance with differences not exceeding 10%. In contrast, comparing ferrous-based shape memory alloy and steel, we can say that ferrous-based shape memory alloy shows a significant advantage with margins exceeding 7 times. In general, ferrous-based shape memory alloy remains the most cost-effective option, offering almost the same benefits as the more expensive nickel titanium based shape memory alloy. Now, the next section is about conclusion. So, in conclusion, this work showed the unique properties of shape memory alloys, focusing on shape memory effects and superelasticity, and also their applications in helical springs and seismic reinforcement of buildings. For the springs, simulations showed how different factors affect their behavior. For seismic reinforcements, ferrous-based shape memory alloy bars showed many advantages, such as reducing the residual deformations, improving building performance, and offering a cost-effective option. However, challenges like high costs and complex installation still exist, and further research is required for broader use. For the perspective, we aim to explore the application of shape memory alloy reinforcements in the irregular structure. This will help us understand how shape memory alloy can improve the seismic performance of structures with complex geometries. Next, we plan to expand the analysis from 2D to 3D. This shift will provide more accurate results, capturing multidimensional seismic effects. Finally, by analyzing different bracing systems and configurations such as X, V, and inverted V, we aim to understand their impacts and how they can improve seismic performance. Now, moving on to my publications. The first one was accepted in 2021 under the title Force Displacement Relationship for Nickel Titanium Alloy Helical Spring by using ANSYS, Superelasticity and Shape Memory Effects. The second publication is Improving Seismic Performance of Reinforced Concrete Structures by using Ferrous-based Shape Memory Alloys, was presented in MATIC Web of Conferences in 2022. And finally, my most recent work is the seismic performance of 2D regular reinforced concrete frame buildings strengthened by using shape memory alloys, and it was published in the International Journal of Engineering Research in Africa in 2024. So this is the end of my presentation. Thank you so much for your listening. If you have any question, please feel free to ask.